Lecture 11 covers sections 5.1 through 5.2. At the end of today's lecture, you should be able to represent physical systems in terms of our equilibrium equations through the construction of free body diagrams, denoted as FBDs. We're going to focus on the construction of FBDs today. A discussion of equilibrium equations will follow in Lecture 12. And you should also be able to understand the basic types of supports used when analyzing our static structures. Let us begin by talking about how to construct a free body diagram, and we have a standardized procedure for doing such. First, we have to decide which body or groups of body are going to be analyzed, and we're going to isolate said body or bodies from our surroundings. Then we are going to denote the direction and location of all applied forces acting on our body. Lastly, we have to denote the direction and location of all reactionary forces acting on our body. Now note, applied and reactionary forces differ. That is, applied forces are those acting on the system, and applied forces can be surface forces, either a point load or a distributed load, or body forces, such as gravity. And these applied forces want to cause our body to translate and or rotate. Now, reactionary forces are what arise from our constraints, and these oppose the tendency of our applied forces to cause our body to translate and or rotate. That is, our reactionary forces are required to keep our body stationary, i.e. static. Reactionary forces arise from the type of supports that we use to constrain our body. Now, these forces are denoted with the variable r, and in vector form have r with the vector arrow over top. And we will use subscripts x, y, and z to indicate the direction of said reactionary forces. In this class, we're going to use a variety of supports, and you can follow this hyperlink to look at a large number of structural supports that you may encounter. However, for this course, we will primarily consider fixed supports, pin supports, and roller supports. Now, a fixed support prevents all translation and rotation. That is, the end of our body of interest is fixed. Now, a pin support, as shown below, prevents motion in our principal directions. That is, for a 2D system, our pin support is providing a reactionary force in the x direction and a reactionary force in the y direction. That is, our bridge cannot move in the x or y direction at this pin joint. A pin joint, or a pin support, allows our body to rotate. You can think of this as a hinge. And lastly, a roller support, as shown in the figure below, allows movement in the direction that is parallel to the surface that our rollers are situated on. However, it prevents movement in the direction perpendicular to the surface that our rollers are sitting on. And you can think of this as a roller blade. What's nice about a roller support is our body is able to translate and rotate. However, our translation is typically limited in one of these directions. For the example below, our roller joint provides a reactionary force in the y direction. However, our bridge is able to move to the left and right, as well as rotate about this joint. When we describe our reactionary forces, we have to be intuitive. That is, when we have a support acting on our system, the reactionary forces that this support is providing has to be physically realistic. That is to say, it would run contrary to our intuition that the roller support in the previous slide would behave the same as our pin support. They are two totally different supports and provide different reactionary forces to our system. Now, in our two figures, we aligned our reactionary forces with our principal directions. That is, Rx was acting in the positive x direction, and our Rys were acting in the positive y direction. However, you can guess the direction. It will not matter if you guess Rx to be in the negative x direction and Ry to be in the negative y direction. For, as you will see in Lecture 12, once we solve our equilibrium equations, a minus sign will be associated with that reactionary force. And recall, our reactionary force is a vector. The minus sign tells us that our direction needs to be flipped. Now let us look at a basic example of a fixed support. That is, we have a beam that is fixed to an immovable wall at point A. Where would our reactionary force be applied? Well, our wall is providing a reactionary force. That is, we will have Ry existing at A. In what direction would this reactionary force exist? In the positive y direction, to counter out the 250 Newton force acting in the negative y direction. What would the magnitude of this reactionary force be? We would assume it to be 250 newtons, to counteract the 250 Newton applied load at B. And is there any other reactionary phenomena that would be required to keep our beam static? Now, we know from our discussion of moments that there is going to be a moment of force about point A due to the application of our 250 Newton force at point B. That is, our 250 Newton force is going to create a clockwise moment. Thus, our wall must apply a counterclockwise moment of the same magnitude about point A for our body to be in equilibrium. We will discuss more about this in Lecture 12.